So last time we were talking about Schrodinger Equation and operators. So maybe I can start by a small review. So the operators and wave function. So it's interesting that we introduce as a main object, which we would like to study, some function, which can be function of position and time. So this would be the main object for us, not x as a function of time, not velocity as a function of time, but distribution. And more accurately is amplitude of density of probability of finding your particle around position x at time t. So we were talking about how we make interpretation of this wave function. Yeah? This is the main object. So this main object must have an equation from which we can derive this wave function. And this is called Schrodinger equation. This is a non-stationary form of this Schrodinger equation. And then I'm going to introduce operators later, but now I'm going to just write it in 1D through the partial derivatives. So this term represents me kinetic energy, and there is another term which represents me the potential energy of the system. So then you're gonna get solution of this equation, and this would be your wave function. And this is the one big part of this. So the second part, once you get solution of this equation, what kind of prediction you can make? Like, can you tell me what will be the position of the particle? Can you tell me how fast the particle will be moving? So something I can compare to the experiment. Yeah? So then, because we don't make observation of wave function itself, we can get it from solution of Schrodinger equation, but we don't really measure wave function. We measure something like position or energy levels or whatever. So how can you extract position from this? Well, you can say average position, for example. And initially you can write it as a position multiplied by probability. And this is a probability, yes, to have this position. But what about if I want to calculate average velocity? And this is when it becomes more interesting. So, for example, we introduce what's called operators. So instead of talking about position, in quantum mechanics, you introduce the operator of position. And I put this hat on top. So this hat represents me this object is not a number, it's not a function, it's an operator. And the operator can act on wave function. So then the operator for position would be just multiplication by x. It's a very simple operator. And for example, operator for momentum is less obvious. So I'm going to write it and remind you, minus I h bar d over dx. So this is an operator. It's a rule, basically, how you change a function. So for example, if you have operator and you apply it to some function, so then you just apply this rule to this function, and the result of the application would be the partial derivatives from this f. So you see, it's an operator. And how you act with operator x on wave function would be just multiplication by x. So you have a function, then you apply operator, and this is the result of this action. So basically, there is a more strict definition of operators. You usually have to define what kind of functions you act on. For example, our functions should be normalized, so they should be integratable. So then, once you introduce operators, you can extend a little bit the meaning of average values. So you can say the average momentum would be an integral between psi conjugated xt. Then you put an operator here on the momentum acting on psi. So, and the same you can write for x operator. Psi conjugated operator psi dx. So we can take it as something given to us. So then we have a complete picture right now. So my main object, which I'm trying to work with, is a wave function. I know equation which this wave function should satisfy. Instead of physical quantities like position or momentum, I'm going to introduce operators. And something I can observe, it would be average position or average momentum. So then it would be average from these operators. So then this is the last point. And it kind of formulates a new theory. It's completely new theory. If you try to compare this theory to what you know, to what you have before, it is completely different. Well, before you have x as a function of time, you can take derivatives, you find velocity as a function of time. You have acceleration, you have second Newton law. It's completely different. Well, maybe as a part of review, it's enough. Yeah. So we can move on starting from this point. Do you have questions? Maybe I also can introduce a couple more operators, maybe later. Okay, let's move on. Let's talk about something, it's called uncertainty and eigenvalues. So eigenvalues, values and eigenvectors. It's another relatively new element to you. And maybe some of you have heard about eigenvectors and eigenvalues. In this case, I would call them eigen functions. So the eigenfunctions and eigenvalues are a very important part of quantum mechanics. It helps you understand better what's going on. So let's say you have an operator. It doesn't matter what operator. I can just pick t hat. I'm going to call this an operator. Then we can take a linear momentum operator or energy or position or whatever. So from this operator, I can find the average. So the average would be an integral from psi star operator acting on psi dx. Yeah. Maybe at this point I can introduce short notation to this. Psi function on my left side, operator, and psi function on the right side. So this would be representing the average from this operator. This notation is slightly shorter than if I have to write every time the integral. But they're just identical, they represent the same. This is called bracket notation. This is a bra vector, this is ket vector, and this is operator. Kind of bracket notations. But if you don't like it, I can just write normal. So what would be the uncertainty of these operators. Uncertainty. Well, or standard deviation, yeah? You have to calculate average from operator square, and then you subtract average from the operator square, and you want to take a square root from this, and this would be uncertainty. So the meaning of this uncertainty is the following. So let's say you have a possible values for t, and then you have some average value, and you have uncertainty. And we can think about it. For example, if I pick operator x, then it would be average position and uncertainty in position. And this should be probability, yeah? Or density probability. So basically, if your uncertainty is very small, what does it mean? For very small uncertainties, it means that your distribution kind of has a small width. So you have a more or less certain value. And opposite to this would be, what if you have a very large uncertainty? Then it's very hard for you to tell what is this value of this. So you have uncertain value. So then this becomes a very important parameter, and this parameter can be calculated as mentioned here. Yeah? You need to calculate average from t square, and then subtract average t square and take a square root. It's a standard, it's called standard deviation. Yeah, it's a standard statistical approach. What does it have in common with eigenvalues and eigenvectors, and what does it mean, eigenvectors and eigenvalues? So what if you have operator, you act on a function, and you get the same function? Maybe with some constant in front. Have you seen this in your life, this type of equations? So you have an action, you apply it to a vector or to a function, you get the same function with some constant. Have you seen this equation before?
Yeah, theory, like exponent theory, right?
In some calculus class, you probably have it for matrices.
It's a linear transformation.
Yeah. So then this equation for eigenvectors and eigenvalues of operator t. So I can put a small label lambda. That means that this function will correspond to this value lambda. So if you can find solution of this equation, then you would say my phi lambda is eigenvector or eigenfunction. And lambda itself eigenvalue. So then if you have operator, any operator, you can try to formulate a problem and find the solution for eigenvectors and eigenvalues. And in many cases, you can find many solutions to this equation. So you can have a different lambda and different eigenvectors. Or sometimes you can't find any solution. So it depends on your operator. Now, I know it sounds a little bit abstract to you, but I would like to demonstrate why it's important for quantum mechanics to formulate and have solution for such a problem. And I can relate it to the Schrodinger equation. So for example, let's say you have a psi lambda is an eigenvector of operator T, eigenfunction of T. Then when you calculate average T, what you're gonna get? I'm gonna use this bracket notation because it's shorter to me. So you have a average operator psi lambda. So when you calculate average from this operator over eigen functions, what you gonna get? We can use this property because we can say if this is eigenfunction, then operator T acting on this function will give me the same function. Can I use this property? Do you understand that this operator acting on the wave function psi lambda? Or these bracket notations are too confusing for you? Do you want me to rewrite it? Something like this, yeah? Still, I would like to go back to bracket notations. Brackets notation. Can you tell me the result of this average? Operator acting on the wave function. Can I replace it with just a lambda and this wave function? Is it obvious?
Is it lambda squared or just lambda?
This is just lambda, yeah.
Lambda, okay.
Operator applied to this function will give you the same function as some lambda. So then inside the integration, I can say when operator T is acting on wave function, I'm gonna get psi lambda, lambda, psi lambda. Yes? Yes. Can I move this lambda out? Because lambda is constant, yes?
Yes.
Yes.
Then if I move it out, I'm gonna get just integration psi with itself. Let's assume that my wave function is normalized. Then this integration should be equal to 1. Because basically it's a psi absolute value squared dx. If it's normalized state, then it should be 1. Then I'll get an interesting result. That if you take average from your operator over eigen function, you're gonna get eigenvalue. So this would be the meaning of eigenvalue in a sense. So average from operator over not just any state or over special state, eigenfunction will be eigenvalue. So the meaning of this eigenvalue is an average for this operator over this state. But actually it's even more deep than this. What if I calculate average from operator square? So forgive me, I'm going to use bracket notations. I'm going to say my t square is when you apply operator t twice. This is t square, yeah? Can I act with this operator? One time and then second time. Similar like what I did here. What will be the result? When I apply operator first time, what I'm gonna get?
Lambda times lambda, right?
Yeah, operator T will stay, and this operator, the first one will be replaced with lambda. Make sense? What if you continue? What if now lambda you can move it out? It's a constant. What happens if you act one more time? You're gonna get
lambda again, lambda square.
Lambda square.
Lambda square.
Plus maybe the normalization integral, which is equal to 1, yeah, because you're gonna go up psi and psi at the very end. And if it's normalized state, it will be 1. But even if it's not normalized, it's still okay relative to the point I'd like to make. So then this means that average from this operator T in any power can be lambda in this power. Basically, that's it. So, yeah. What will be the standard deviation? The standard deviation was a square root from average T square minus average T square. What is my average T square?
Lambda square.
What is average T?
Lambda square.
So what will be the standard deviation? What will be the uncertainty?
0.
0. Suddenly, it makes interesting sense. If you have 0 uncertainty, what does it mean? Then in this quantum mechanical state, the value for this operator T is certain. So the conclusion from this would be, if psi lambda is an eigenstate. Okay, I confuse, it's all the same. Eigenstate, eigenfunction, eigenvector. They represent the same object. Eigenstate, eigenfunction, eigenvector. An eigenfunction of a operator T. Then, in this state, I mean psi lambda, T, the value T, is certain. You don't have uncertainty. Then you don't have any possibility to find other values. It will be very certain value. Does it make sense? So then when you solve this equation, the second conclusion, if you try to find the solution of this equation, you basically trying to find such states in which this quantity has certain value. So it will give you set of eigenfunctions and eigenvalues. This would be possible values and possible states. Values of operator T and possible states. So this equation becomes very interesting because it gives you a chance to calculate what are possible values and what are possible states that this quantity T may have. I'll try to give you a couple of examples. So we can try to to understand what all this means. But the idea of this equation, I hope it is clear now. Yeah? Idea of finding eigen functions and eigenvalues for any given operator. So a couple of examples. What if my operator is P? Can I find eigenvalues and eigenfunctions of operator P? If I can do this, then this would be possible values for linear momentum, and this would be states in which I have certain linear momentum. And because it's linear momentum, people usually replace lambda with P. And this P is number. It's a value. And this P is operator. So my question is, can I solve this equation and can I find possible eigenvalues and possible eigenstates? Yeah, it's relatively easy. Do you remember what was the operator for linear momentum? It was negative I h bar d psi over dt. Oh, d psi over what?
dx.
Dx, yeah. Then it will be equal some value, which I call eigenvalue, and the same function. Or I can rewrite it maybe like this. D psi over dx would be equal plus p h bar psi. So what kind of function should be? So when you take derivatives over x, you're gonna get this coefficient in front. What is the solution of this equation?
It's an exponential.
It's exponential. Can you tell me what kind of exponent is this?
IP over h bar x over, yeah, times x, yeah.
There could be some constant of integration. And constant of integration will be just in front. Because it's eigen function, it corresponds to certain eigenvalue. So I can put p here instead of lambda. So the coefficient in front can be any function of time. So then I can say that this is a possible function of x and time. So this is going to be state which has certain linear momentum, and this is my linear momentum. It's a plane wave, yes? So it's a combination of cos and sine function. So it's going to be cos function px over h bar plus I sine function px over h bar. So basically this is just plane wave, yeah? So plane wave has certain linear momentum. This is not something very new to us. And actually we have seen this before, yes? Because p over h is a wave vector k. So this is a cos kx and sine kx. It's a Louis de Broglie formula. It's just a plane wave. So now interesting that this state has certain momentum, but position of this particle will be very uncertain. So if you try to plot cos or sine function, then cos or sine function as a function of x, I'm going to plot maybe cos function, yeah? Will look something like this. From minus infinity to plus infinity. So this state will have certain momentum. What about position? Can we tell where particle is? No? It's a wave. Yes, particle is what is the position of a wave? Plane wave. It's everywhere. Yes, there is no position like of a particle. Let's have another example. Operator of energy. I h bar d over dt. If I try to solve eigenvalue problem for this operator, then the meaning of eigenvalue would be possible energy, yes? So let me just change it to E. Okay, what could be the solution of this equation? So let's try to plug this operator, and then what will be the action of this operator on the wave function? I h bar d psi over dt equals E psi, yeah? Or we can say d psi over dt equals minus I E h bar psi. What kind of solution of this equation? Now it's derivatives over time. The solution with certain energy. From, yeah, go ahead.
Cx and exponent minus IET over h bar.
This is called, okay, this is eigen function of this operator. The interesting part, interesting property of this eigenfunction, if I try to find absolute value square, the distribution, then you're gonna get a C conjugated exponent. I take conjugation as I E t over h bar multiplied by C exponent minus I E t h bar. So you see the exponents will gonna cancel out, and you will have C as a function of x square. So then whenever you have a state with certain energy, then the corresponding distribution is not going to depend on time. This is called stationary solution. The wave function does depend on time. That's okay. But because it has certain energy, so it's eigen function of operator E, then the corresponding distribution is going to be stationary. So that means when you have electron or particle distributed like this at some time, then this distribution will stay the same for the rest of the evolution. It's a stationary solution. There is a deep meaning behind it, because you're saying that once you have a certain energy, it corresponds to stationary solutions. So then having certain energy and having stationary solutions become identical in quantum mechanics. It's very interesting. This is another example of eigen function and eigenvalue for another operator. Sometimes you can find what if my wave function corresponds to satisfy two equations, p psi equal p psi and e psi equal e psi. Can we try to solve this equation? So what will be the meaning of this equation and solution? That the wave function has certain momentum and energy at the same time. Certain p and energy at the same time. And sometimes you can answer yes, we can do this. But sometimes you can say, no, we cannot do this. For this particular case, apparently we can do this, yeah? We can do it. The solution would be like this. Some constant, now it's just real constant, it's not function of x or time, exponent minus I et over h bar plus I px over h bar. So you see, it's at the same time, it's eigen function of energy operator and eigen function of p operator, linear momentum operator. So sometimes it's possible, but it's not always possible. We cannot find solution for this situation, for example. What if I would like to have certain position and a certain momentum? So is it possible for a particle to have certain position and certain momentum at the same time? No. It's not obvious at this moment. Maybe later I can show you. It's called Robertson-Schrodinger identity or equation or theorem, when you can show that this combination of two equations has no solution. So the result for this Robertson-Schrodinger statement is that uncertainty in x and uncertainty in momentum always should be greater than some minimum value. And this is called Heisenberg uncertainty principle. Heisenberg uncertainty principle. So you see, sometimes it's possible to have several values certain in your wave function. Sometimes it's not possible. I would like to comment on this Heisenberg uncertainty principle. So then how it's possible that you can't have a position and momentum at the same time? So let's say you have a certain momentum. Your wave function looks like a plane wave. So you have certain momentum, yes, but you don't have position, certain position. Your position of your particle is uncertain. What if you combine several waves? You have a higher momentum, oh, wait a second, it's lower momentum, yeah? It's a longer wavelength, meaning lower momentum, and maybe even lower momentum. What if you add them? Then as a result, you may have a superposition, you add them, so your wave packet may look like more localized. So you have a delta x. So in principle, you can localize your particle at some scale delta x, but you have to sacrifice. You have to combine waves of several linear momenta. So then you can have a higher, you have to higher momentum, you have to add higher and lower momentum. So then you have certain delta p here. It says how many different frequencies or wave vectors or linear momenta you have to combine to build a wave packet which has certain delta x. So then this uncertainty principle means something simple. If you have very certain delta x, so if delta x goes to 0, so that means you want to build a very certain position, then delta p will go to infinity. If you want to build a wave packet which has certain position, you have to combine a lot of different linear momentum. So then what kind of momentum you will have, you don't know. what if you have a very certain momentum? Well, it means that you have just one wave, yes? What will be delta x? What will be the uncertainty in position? Infinite. You cannot have both of them small. If you have very small delta x, your delta p will be large. If you have a very small delta p, your delta x will be large. The product should be always greater than the Planck constant over 2. I believe we're going to come back to this question because this uncertainty principle is very interesting. Today I want to just talk about eigenvalues, eigenfunctions, and how they related to this certain uncertain values for an operator. Does it make sense? Do you have questions? So far so good, yeah? Let's have another operator. Let's look at the Schrodinger equation now. Schrodinger equation, operator of energy applied to psi x and t will be equal what we call Hamiltonian applied to psi x and t. This is a short notation for what we had before. Yeah? Then you have all this minus h bar to m, second derivatives over x squared plus u. You can look at this as an operator acting on the wave function. And the wave function is a function of x and time here. So this combination I'm going to label as H, and it's called Hamiltonian. So basically, the first term inside Hamiltonian is a p squared over 2m. This is kinetic energy. The second term is potential energy. So altogether, it's a mechanical energy. So Hamiltonian is a mechanical energy. Mechanical energy. When you write it as a function of p and x, as a function of p and x, and you replace p with operators. So kinetic energy and potential energy. So then we can look at this equation from a different point of view. So this is my Schrodinger equation. So what if I would like to have stationary equation? So stationary solution. For stationary solution, operator energy applied to wave function must be equal E, some energy, and the wave function itself should be some function of x multiplied by exponent minus E energy time h bar. Yeah. So we already have solved this equation before. This is a solution of eigenvalue problem for operator E. So for the left side of the Schrodinger equation. And you can look at this as a non-stationary just Schrodinger equation, or you can try to find what we call stationary equation, solutions which have certain energy. If you plug it back into equation, what you're gonna get? When operator E acting on this wave function, you're gonna get E exponent minus I E T h bar phi as a function of x. This is the left side of the equation. What about the right side? You have operator H, which is a shortcut for all of this inside square brackets, acting on the same wave function, which is exponent minus e and phi. Can I cancel this exponent? Let's say my operator H, Hamiltonian, let me cancel constants. This is like a constant, yeah? Because operator x only on x coordinates. We don't care about time. So time is like a constant here. I can cancel this. So what I'm gonna get as a result? I'm gonna get something like this, yeah? And this is my stationary Schrodinger equation, if you remember. This was a time-dependent Schrodinger equation. This is time-independent Schrodinger equation. This is problem for eigenvalues and eigen vectors of operator H. So you see these eigenvectors and eigenvalues are everywhere. They're very important. So then, for example, you can write solution of Schrodinger equation like this. You can say stationary solution. One more time. Solutions. You solve this equation, operator H acting on function only x equals some constant function of x. Then once you solve this equation, you're gonna get a set of possible eigenvalues and eigenvectors. And then the psi as function of x and t, which has certain energy, will be this exponent and multiplied by phi. This is already a solution which we will call stationary solution, because if you take absolute value square, so when you calculate the distribution of your particle in space, then the exponent will cancel out and you will have just phi e as the function of x squared. Yeah, time independent. I hope I convince you that this, when you bring this new philosophy, like you're talking about operators, then the very natural next step would be to study problems for eigenfunctions, eigenvalues for each operator. So the Schrodinger equation itself is an equation for eigenvalues and eigenvectors. The result of solution of the Schrodinger equation would be a set of possible energies and the corresponding quantum mechanical states. And this solution will represent me stationary states, which when distribution doesn't depend on time. And this would be the full solution when you have time dependence, but your time dependence would be simple. So of course this solution would satisfy the main equation, a time-dependent Schrodinger equation, when you have just derivatives over time. So all I have to do is just to solve this time-independent or stationary Schrodinger equation. As a result, I can get quantization of energy. I can get allowed energy levels. For example, if I write this problem for hydrogen atom, as a result of the solution of this problem for hydrogen atom, I should get spectrum of hydrogen, which I can measure on experiment and compare. And if my calculation of this spectrum, energy spectrum for hydrogen and experimental results are coincide, then this is the very good, yeah? This means that my equation describes the experiment. Let's have an example when we can look into more deep details of how you can solve this equation. So we're ready to solve time-independent stationary Schrodinger equation right now. We know what kind of result we expect, and we know how to write the general solution for this time-dependent solution. So before I jump into solving Schrodinger equation like this, do you have maybe questions? How do you like it? Okay, before we move, I would like to underline the last time. In classical physics, we have excess function of time, momentum, and things like this. When you move to quantum mechanics, you replace them with operators. These operators are not functions of time. They're just a way how you can act on a wave function. Plus, you introduce the wave function. So then, to be able to find anything, you need Schrodinger equation. And your Schrodinger equation will look like you have an operator of energy acting on wave function. Will be another operator like mechanical energy, p squared over 2m plus u as a function of x, kinetic plus potential. And this Schrodinger equation should give you the solution for this. Once you have solution, you can find average position, which will be a function of time, but not in this sense like before. Average position will be a function of time because wave function will be a function of time. You can find average p, and you can find any other averages you would like average x squared, average kinetic energy, average potential energy. So you can introduce any operator which corresponds to any physical quantity. So this is basically how quantum mechanics is formulated. And yeah, something like this. So let's do something, yeah? Example. Let's find possible energy. So find stationary solutions, yes? Solutions, stationary states. I would better say states of a particle of mass m in infinite well potential. So what do I mean by infinite well potential? So then you have a x, y, oh, we may not need y. Let's say this is my potential energy. Then you have, let's say at minus L over 2, you have infinite wall. and at plus L over 2, you have infinite wall. Yeah, sorry for these drawings. So that means my potential energy would be equal 0 if particle is inside this potential well. So if you're moving in between minus L over 2 to plus L over 2, so there is no potential energy. So basically it's a free motion. But if you try to go beyond this infinite well potential, then the potential energy will go to infinity. That means it's going to be very hard for you to go beyond this. So you can imagine in classical physics, you have just one wall, second wall, and you have a ball of mass m moving with some velocity v. So the ball will be moving left, right, left, right, left, right. This ball will have certain energy. So the energy of the system will be something like this. The energy is conserved. It's elastic collisions with the walls. So the particle will be moving left, right, and every time you hit the wall, you just change the direction of motion. So you go back. And then you hit another wall, you're moving back. So this is kind of infinite walls, potential walls, yeah? It's not possible to go through the wall for apparent reasons, yeah? So from classical point of view, what could be the energy of the ball? The energy could be mv squared over 2, yeah? Because you don't have potential energy, you only have kinetic energy. What kind of values this energy or velocity we can have in classical physics? Do we have any restriction for this v in classical physics?
No, you don't.
We don't. So you can have any velocity and there is no restriction, yeah? Well, we're not talking about speed of light and things like this. So you can change any energy continuously from one value to another value. So there is no jumps or gaps in this energy. What about if we solve quantum mechanical Schrodinger equation? This equation, if we solve this, can give us possible energies of my system and possible states. And then I can see what kind of energy I can have if my particle is confined by this infinite well square potential. It's relatively easy. We can just solve Schrodinger equation. The only what I would mention this before start solving this, that when you speak about wave function, I would probably agree before we start that the wave function beyond your square well potential should be 0. So the wave function here should be 0, and after beyond L over 2 should be 0. It may look artificially, but actually if you have a infinite potential energy, the particle cannot go this area. There is no chance to find particle beyond the walls. At this point, it does not sound maybe very convincing, but I'm gonna show you later how we can explain this. And also the wave function should not have jumps. If you have 0 value at this point and at this point, then you may have some wave function, but you shouldn't have jumps. Maybe I can explain this also a little bit later when it will be convenient to me. There is no reason for probability to jump. So let's say you have 0, 0, 0, and suddenly you have a lot. So Schrodinger equation doesn't allow this, and there is a strong reason why. For today, I'm going to just accept it as some conditions which I want to use for this. Okay, we can start solving our first Schrodinger equation. So the Schrodinger equation looks like this. My Hamiltonian applied to stationary states, wave function should be some value and the same function. So we don't know E. It's an eigenvalue for energy, so it can be any. We have no any restriction for this, and we don't know what kind of state we want to find this phi. So the solution of this equation should give us both. So the Hamiltonian, it's a p squared as an operator over 2m applied to my wave function plus potential energy applied to my wave function. Must be some constant which I want to make interpretation as possible energy and the same wave function. Then operator p, just to remind you, minus I h bar d over dx. So operator p square would be minus h bar square second derivative. So then this chi is relatively standard, yeah? It's not a partial derivatives anymore, yeah? It's just derivatives. Then potential energy. Let's keep it as potential energy for now. So this is a stationary Schrodinger equation. Then I'm gonna look at my potential energy. I don't want to find solution beyond potential well, because beyond I know that wave function is zero. I'm looking for solution inside the potential well, but inside potential well, I don't have potential energy. Does it make sense if I say for x inside? This equation can have a more simple form. I can just keep only kinetic energy. Would it be clear? I don't want to put potential energy term because my potential energy is zero for this region. For outside, I don't need equation. I would just say that my wave function is zero. So the second line came from, I would call this physical common sense. So let's look at this with a little bit more attention. Let's rewrite it. So then for inside, I'm gonna have the second derivatives from this phi would be equal negative 2me h bar square phi. And it would be convenient to call this combination as a k value. So I remind you that 2m and e is roughly p square, and p over h bar, and this is a wave vector k. So then this combination is very natural to call k square. It would be just a constant which I would like to label like this. K square. So my equation will change into something nicer. And now tell me, what should be the function so you take second derivatives from this function and you get the same function with a negative constant in front? You have seen this before. maybe if I remind
Cosine?
you, yeah, cosine or sine
Yeah. Well,
from which argument? You're right, very good. So remember this equation for simple harmonic motion. What was the solution of this? Cos omega t plus b sine omega t, yeah? This is the same. Instead of omega, you have k. Instead of derivatives over time, you have derivatives over x. So what will be the solution? I can relatively easy to write possible solution for my stationary states. It could be a cos kx plus b sine kx. You can double check. If I take second derivatives from this, I'm gonna get the same function with negative k squared. Every time you take derivatives, k will go out. That's how you can get k squared. Derivatives from cos function is minus sine. From minus sine is again cos. Oh, minus cos, yeah. And the same for this one. So we're almost done. This is the solution. We just solve Schrodinger equation. Not until the very end yet, because we did not find possible energy. We just say this is a solution of this differential equation, and my constant k inside can be related to the energy. And so far I don't have restrictions for energy. So energy can be any, constant k can be any. It looks fine to me. So the solution will look like this then. If you go beyond potential well, you should get 0. If you inside, you can get either cos kx or maybe sine kx. So outside we know that there is no chance to find particle, and inside it could be some harmonic function of some k, and at this point k can be any. I don't have any restrictions for k or energy. But then I would say my function should be continuous. I shouldn't have jumps. So my solution inside must satisfy certain conditions on these borders. So then this is good, but I'd like to have continuous solution. So then I have to work a little bit more on this. So the work is not done yet. But we did the main part. We already did a good job. So let's move on a little bit. Let's talk about what can I do to make it continuous at the borders. And now I would say, let's talk about even and odd solutions. So we have certain symmetry. So due to symmetry, we're gonna pick even solution. An even solution would be a cos kx, and we're gonna have odd solution. Let's say b sine kx. So actually, why I can treat them separate. They have different properties. One is so the symmetric solutions or even solution, they will look like this. So the left side and right side are identical. So this is going to be my even versus something like odd solutions. maybe like this. What? I can explain this actually in more details why I can do this. There is a theorem behind it. But for now, just trust me on this. I want to get to the answer. Then let's consider them separately. So even solutions. Even. For the even solution, my wave function in between inside the well would be a cos kx. And I have to say that when I plug x equal L over 2, plus or minus, then I should get 0. Yeah. When I approach the wall on the left or on the right side, this solution should come to 0. This is important to me. I would like to have continuous solution. So when you approach the wall and then you want to continue with 0, you can't approach it like this and then jump down. Then I'm gonna apply this condition. What I'm gonna get is cos k L over 2, plus or minus doesn't matter because cos is even function, should be 0. When it can happen? What is this? What is the solution for this equation?
L over 2 is pi over 2.
So this means not all
N
k.
pi.
Yes, Amar, go ahead.
No, sorry.
Pi over 2.
Pi over 2, yeah. Or maybe 3 pi over 2, yeah?
Pi over 2 plus k pi.
Okay, let's write a more general equation. It's pi over 2 plus integer number of pi. What does it mean? It means that for some k, the very special k, I can satisfy this condition and I can find solution. But if my k doesn't satisfy this condition, then I can't find continuous solution. I can't find solution for my Schrodinger equation. This is a moment when you have quantization appears. Not all possible k are possible. Not all k are possible. And k is my energy. Restrictions on k means that not all energies are possible. This is a very important, this is a crucial part. Not all k can give you a valid solution for the Schrodinger equation. There is only very special k for which cos will be equal at L over 2. Only for this k you can find something. It's very interesting. So we can say, okay, you have a k L over 2 equals to pi over 2, 1 plus 2n, when n equals 0 or 1 or 2 or 3. Basically, I can write it like this, or maybe it will be more convenient if I rewrite it in terms of just pi over 2n, big N, where n is going to be some odd number. 1, 3, 5, 7, 9, blah, blah, blah. So then these are equivalent. I don't like to write 1 plus 2n, I would rather write capital N. So then, what should be possible k? Well, factor 2 will cancel out, yeah? Pi n over L, yeah? So then my solution would be some constant cos, and before it was kx. Now I can say it's going to be pi n over L and x. And you have a solution with different n equal 1, n equal 3, n equal 5, 7, 9. You have different solutions. What could be energy for this solution? This is the eigenvector, yes, it's eigenstate or eigenfunction. How can I find energy? Yeah, energy, where is my energy? Energy can be related to vector k. So energy will be k square h bar square over 2m, yeah? K square h bar square over 2m. So then the corresponding energy would be pi square. I'm trying to make k square, n square h bar square over 2m L square. The coefficient A can be found if I ask that my solution is normalized. I don't know if you understand it or not, but we just found allowed energies for my system. So only En are allowed. We have a spectrum. And if I can rewrite it a little bit, I'm going to put as a constant pi square h by square, and then dependence on n, which is integer number, yeah? So my spectrum will be proportional n squared. I have a minimum possible energy. I have n equal 1. I can have lower than n equal 1. I can have n equals 0, for example. I am not allowed to have zero energy here. I have quantization of energy. I have a spectrum of possible energies. And each energy, for each energy, I have the wave function. This is the solution of eigenvalue problem with my Hamiltonian operator. Just to be complete, that was even part. Can I do the same for odd functions? Because I want to have a complete solution. So then odd solutions would be sine kx, and I have the same condition. When you have plus minus L over 2, you would like it to be 0, which gives me the sine k L over 2 must be equal to 0. And when this can happen, my k L over 2 must be equal to
n pi, where n maybe 0, 1, 2, something, yeah.
n can be, okay, n can be, n equals 0 is a strange solution, but the other one are good. Why I don't like n equals 0? Because if your n equals 0, that means your k equals 0. When k equals 0, it's just a 0 solution. I don't believe that if your solution phi equals 0 is a good something good. So I would just cross it out. Even if you satisfy this equation, but it would be too trivial. That it's not like a, you can't normalize this solution because it's just 0. But the rest looked nice to me. Yeah, very good. So then I can write something like this for KL, for vector K, not that vector, value K, for odd. So then my K would be equal to pi to n pi n2 over L. If I compare this to previous one, what I had before was something like this, and my n was 1357, yeah? Then was like odd number. What I have right now, it's pi even number, yeah? And the same L. Can I rewrite it in the same pattern? So can I write it like this? Pi big N over L, where n equal 2 or 4 or 6 or 8. So basically it's going to be an even number. In this case, my K will look the same form as this one. But different n will correspond either to even solutions or odd solutions. So then energy for this would be the same, pi square h bar square 2ml square n square, and the wave function would be b sine k n lx. And again, my n equal 2, 4, 6, 8, and so on. This is the end. So you have a spectrum, and for each n, you have a wave function. So if n is even, then your solution would be cos if n is odd, then the solution would be sine function. So now I would like to look at the energy spectrum and what kind of solution we have. Let's analyze what we have. You have this infinite square well potential. Minus L over 2, L over 2. So the energy spectrum we get is pi square, h bar square, n square over 2m L square. So the lowest possible energy would be for n equal 1. So n equal 1, I have the lowest energy. And sometimes it's called ground state energy because it's the lowest possible energy. So then it's going to be just pi square, h bar square, 2ml square. And it would be my cos function because it's a symmetric solution, it's an even solution. So then you have 0 here, you have 0 outside, and you have just cos function. You have half of wavelengths. It's like a standing wave. And this would be the energy of this solution. What about n equal 2? What will be my energy for n equal 2? I have to plug n equal 2, yeah? So maybe 4 times. So maybe I can make a spectrum here. Energy 0. You have a ground state. Then the first excitation when n equal 2 would be maybe 4 times greater. E2. What kind of wave function we will have for n equal 2? Can you imagine? It should be sine function, yeah? Because when you have odd number, oh, I believe I confuse it, yeah? It's my bad. This should be odd, and this should be even. When n equal 1, it's a cos. When n equal 2, this is sine. Then you're gonna have something like this. What about n equal 3? So energy will be 9, yeah? There is gonna be even solution. How can you imagine the wave function for this n equal 3? It should be symmetric, yeah? Like this. And so on. We get quantization of energy. Not all energies are allowed. You have a minimum possible energy which is non-zero. Then you have a gap. So in between these two levels, the energy is not allowed. Particle cannot have energy in between. Only ground state or E2 or E3. Then you have another gap for E3, E4. This is called quantization of energy, yeah? So if you come back to this classical picture when you have a moving ball, then from classical physics point of view, you can have any energy. Even you can have zero energy because you can stop it. But from quantum mechanical point of view, you cannot stop it. There will be at least some minimum energy, ground state energy. And from quantum mechanical point of view, you cannot have any energy, only very specific energies. Like this. So n can be equal 1, 2, 3, 4, and so on. An integer number. N equals 0 is not allowed. So we just solved completely a pure quantum mechanical problems. we found solution of stationary Schrodinger equation. We found infinite number of solutions, by the way, because this n can be any number. For each solution, we have a energy, eigenvalue, and we have a wave function. And if you want to have a stationary solution, you would keep it like this, or you can do something like this. You can say a time-dependent solution would be, you just have to add time dependence, yeah? So this would be solution of time-dependent Schrodinger equation with time dependence. And this is solution of time-independent or stationary Schrodinger equation. So your energy is equal to, one more time, yeah, pi square, h bar square, n square, 2ml square, and n equal to 1, 2, 3, to infinity. How do you like it? Questions?
Very nice.
Thank you. Now, let's try to understand this solution, because we spend so much time working on this, yeah? It would be good if we can have some message to take home to understand this solution, at least a little bit. For example, let's say do some estimations. Estimation 1. If my m is equal 1 kilogram, so I'm talking about macroscopic object, yeah, macroscopic object, like 1 kilogram ball. The size of the potential well, the distance between the walls, let's pick 1 meter. What would be the ground state energy? And what would be N if energy is 1 joule? Can you help me, if you have calculators? Can we do a brief estimation? So let's say I'm talking about macroscopic classical object. Rigid ball, bounce of 2 walls without losing energy. 1 kilogram, 1 meter. If I'm talking about quantization, then what will be these gaps in between levels, and what will be the ground state energy? Can we do the estimation? Pi square, h bar square is 1.055 10 to minus 34, yeah?
Mm-hmm.
Square to 1 kilogram, 1 meter square. Roughly, what I'm gonna get. Pi square is roughly 10. 1 square I would ignore. 1 over 2, okay, 0.5. 10 to minus 34 square. 68. And you have this 10 from pi square. Ten to negative 67 joules. What does it mean for us?
I mean that you can have zero energy, basically.
This is one.
Not zero, but it's
practically zero, because you can't distinguish it from zero. But there is another also consequences. When you have these gaps between energy levels,
they were so close.
The typical gap is integer number from this ground state energy. So the gap will be 10 to minus 67 or 10 to minus 68 joules. Even if you have these gaps, for 1 kilogram body. Can you possibly feel or measure that energy is quantized?
It just continues.
This just continues. And then can you ever know that you have a ground state energy which is non-zero? No. Because when you try to measure this, you put a device which can measure energy. This device will measure a lot of levels at the same time. You don't have such fine device to distinguish such small energies. So then, what is the prediction of quantum mechanics for macroscopic objects? Technically, yes, you have quantization of energy, but practically, the energy is continuous. There are no gaps. Or gaps are so small, then there is no even a chance to ever measure these gaps. So then when we treat classical objects through classical physics, we are completely fine. It doesn't contradict quantum mechanics. It doesn't contradict quantization of energy. Did I convince you in this?
Mhm.
The second question, what if I want to give it some reasonable value for energy? What should be the quantum number n if my energy is close to 1 joule? Okay, now I may need your help, but so energy is 1 joule, m is 1 kilogram, L is 1 meter, pi square, e bar square. So just plug 1 joule, 1 kilogram, 1 meter. Don't forget Planck constant. What would be roughly the n number? What it's called quantum number. If I would like to have my ball, 1 kilogram ball, having 1 joule of energy. My expectation then, because this is 1, this is 1, this is 1, this may be 1 over pi, okay, 1 over pi. But basically I have 1 over Planck constant, yeah? I have 10 to power 34. Yeah?
So I got 4.27 times 10 to power 33.
Yeah, maybe 33, maybe 34. Yeah, it's close enough. This is a huge number. How would your wave function look if you have n equal 10 to power 33? Remember, your wave function is oscillating, and this is a wave vector k. K is, let's find the wavelengths. If this is my wave, yeah, we're talking about wave, then the wavelengths would be, if I can understand it correct, 2L over n. By the way, these are standing waves, yeah? These are harmonics of a standing wave. Your wavelength will be 1 over n. N is 10 to power 33. So your wave function, psi square, yeah? Let's make it square. For n 10 to power 33. You have 10 to power 33 half of wavelengths here. 10 to power 33 between half meter and half meter. Can you measure these oscillations? So your wavelength is 10 to minus 33 meters. can you have a device which you can put inside, and this device will measure quantization in space? Your device must be sensitive to distances like 10 to minus 33 meters. Most likely you have like a finger with nail, yeah, like if you put this finger inside, you're gonna measure some average, and on average, you're never gonna see this up and down, yeah. On average, you're gonna see some constant. So, and I would say if you have a ball moving between left and right walls, then it's pretty probable to find this ball everywhere. If you randomly catch the position of the ball, then with equal probability you can find it everywhere. So then the average from the distribution would be just constant. So then we see there is a connection between quantum mechanics and classical physics. They are not completely deny each other. Quantum mechanical solution for a macroscopic classical object makes sense. You do have quantization of energy, absolutely. You have ground state energy. You have a distribution in space which is less trivial. But practically speaking, it's not possible to measure. And simply because of Planck constant. Planck constant is very, very small. So this 10 to minus 34 basically kills everything. What if I try apply this quantization to a microscopic object? So what if m, it's a mass of electron? What if I'm going to confine this electron at the size of atom? What could be the ground state energy? Now I'd like to talk about a microscopic object like an electron, confined on a scale of atomic scale, yeah, scale of an atom. Can you help me? Can we find the possible energy for an electron in this infinite square well potential? So one more time, pi square ground state, yes, pi square h bar square 2m L square, pi square 0.5534 square. So this 10 to minus 68 is going to stay. It cannot disappear, but it will be compensated by the mass, which is 911 10 to minus 31, and the small distance, which is half 10 to minus 10 square. So at least I have 10 to minus 31 and 10 to minus 20, 10 to minus 51, and maybe even more because of the 0.5. Okay, never mind, 10 to minus 51 and 68. 10 to minus 68 will be compensated by 51. 68 and 51, what is the difference between this? 17, yeah, 10 to negative 17. So far, we're talking about joules. can you help me with this coefficient? You just have to take into account all these coefficients. I would say pi square and 911 goes away. This 2 and 0.5, 0.5 cancels out. Another 0.5 will give me 2. This would be my expectation for this. Maybe slightly more than this. Maybe 3.
All right, I got 2.4.
2.4.
Yeah.
Can you double check the power of 10? Is it correct?
Yes, correct.
This is small. It may be not as small as 10 to minus 67, yeah? That was too small. Can I change it to electron volts? Remember, 1 electron volt is 1.6 10 to minus 19 joules. So how many electron volts here? I just have to divide by this. So I get about 100, yeah? 100 is a little bit too much for me. Okay, whatever.
I got 150.7.
Electron volts. I'm a little bit confused.
Yeah, this it should be 1 point something, right?
Well, this is not hydrogen atom. Yeah, we don't have constant of interaction, alpha constant, the fine structure constant. It could be a correct answer in terms of electron volts. I just want to double check it because it looks for me too much compared to hydrogen atom. So then basically 10 to power 17, negative 17, is it correct or not? 68, this is good. 10 to minus 10, I believe it's half of an angstrom, yeah? And an angstrom is 10 to negative 10. Yes, it should be fine, yeah. Then 51 and 68. Yeah. No, it's fine. I don't see him. But even compared to hydrogen atom, this is a lot of energy.
Yeah.
And for electron, it's very sensitive. Then electron cannot have energy less than this. So for electron, the gaps would be huge. You're talking about different scale, yeah? So let me round this to 150. So, or I can have 0.15 kiloelectron volts. So the energy spectrum then, so you have a zero energy, which is not, you're not allowed to have. The ground state energy would be 150 electron volts. The next energy will be 4 times greater, 600 electron volts. So the next energy will be 9 times greater. So if you have an electron on this level, these gaps, they are huge. So for electron, it's very important that you have these gaps. So then the distribution of electron inside is, well, the energy of electron, the quantization for this is essential. So coming back to the main question, do we need quantum mechanics or not? So if we're trying to solve the Schrodinger equation again, like a Hamiltonian applied to some stationary wave function, you're gonna get energy and this wave function again. Well, it depends on the system. If you're talking about electrons inside atom or this kind of square well potential, which is of atomic scale, then yes, you have to consider quantum mechanics. It's going to be essential. If you're talking about a macroscopic object, 1 kilogram billiard ball, moving in 1 meter square well potential, then do you need to consider quantum mechanical effects? Well, maybe not. Even technically you have them, but you can just speak about normal classical physics. You'll get very accurate result. Quantum mechanics is not going to change anything about it. So that's it. We not only solve the equation, we also analyze this equation. We understand that this quantization that we derived is important for microscopic objects like elementary particles, like atoms, electrons inside atoms. So this quantization may not be important for macroscopic objects because of the Planck constant is very, very small and the other parameters are huge compared to microscopic level. So how do you like it? We can finish. I can just show you one more interesting trick, how you can get this ground state energy without solving Schrodinger equation. I would like to show you how to use uncertainty principle, the Heisenberg uncertainty principle. When you have a particle confined by two walls, yeah, so your wave function should be somewhere in between these two walls, yeah? You don't know, so maybe average position could be 0, maybe not, I don't care. But what can you say about delta x? What is uncertainty of particle's position?
Yeah, L.
L, yeah? We can't really guarantee that this is exactly L, but apparently your wave function cannot go beyond this box. So maybe I can say less than L.
Mm-hmm.
This is very important for me because I know position of my particle with this accuracy. I know the particle is inside. I can guarantee that my particle is inside. So the uncertainty in position of this particle cannot be large.
Mm-hmm.
Then I'm gonna try to look at the Heisenberg uncertainty, that this product should be greater than h bar over 2. If my x is very small, at least smaller than L, then what can I say about delta P? X is less than L, delta X. Then what we can conclude about our knowledge uncertainty in momentum? It should be greater than h bar over L, yeah? Does it make sense? Or it's not clear? It's clear, yeah? Delta X is less than L. Maximum what you can have for uncertainty is L. So that you have uncertainty of momentum greater than h bar over L.
Do we have like times 2?
Oh, factor 2, it doesn't matter, yeah. You can have factor 2, yeah. No problem with this. I'm just trying to make a statement. If your particle is confined at scale L, then momentum, uncertainty in momentum must be greater than h bar over L. It follows from the Heisenberg uncertainty principle. If I'm trying to find the minimum possible energy, for me, the minimum possible energy is a minimum possible momentum. Yeah.
Claro, yeah.
So the momentum, what a minimum momentum I can have? H bar over L, yes? But it will give me some energy, yes? H bar 2mL square as a minimum possible energy. First of all, it explains why you can have zero energy, because if you have zero energy, you have delta X is L and this is zero. Then the left side of the uncertainty principle is zero, but you cannot have zero. It should be greater than something. You can't have zero delta P. That's why you can't have zero energy. You must have some ground state energy which is greater than zero. And second, look at this value. Is it this one? H bar square to m L square, yeah? Of course, you cannot predict pi square. It would be hard for you to do it as constant. Tsai says that we lost factor 2 here. So maybe there would be 8. This is just constant. I'm talking about the scale. Then the minimum possible energy, like a ground state energy, is restricted by this value. You can't have less than this. And you can get a correct order of magnitude for your estimation without even solving Schrodinger equation, just starting from the uncertainty principle. Because your particle is confined, that means uncertainty in momentum cannot be very small. So you must have some minimum momentum at least, which can give you minimum energy. This is nice. This is nice. Okay, I believe we are good for today. Do you have questions?